Alrighty, for our project components, I have a lawnmower wheel because I knew it was already symmetrical and I didn't have to worry about it if it was out of balance, because then we can't use our moment of inertia equations that we have in the book.
It's got constant radius.
Now, when we're using this, we have to make sure that the rope is in the valley here. That way, the radius isn't changing as time goes on. So other than that, this wheel has some grease on it to help make it frictionless as it rotates. Helps us get more accurately data. So other than that, it's just a shaft hooked to a 2x4, which is then held to the table. Now these U-bolts, just holds it on, make sure it doesn't play or slide. And that's about it.
That's it. In our project, Group 1 will be analyzing the planar kinematics of a rigid body, more specifically rotation about a fixed axis, which is a form of relative motion. We were motivated to choose this topic because we covered a lot of these things in our textbook and over the last semester in Chapter 16 as well as in Chapter 12. After solving for angular displacement, velocity, and acceleration, we hope to uncover real-life explanations of what we're learning about in class to further understand the magic behind this topic, eventually leading us to a more solid grasp of these methods. Hanging.
So we have a solid disc right here, right? And what happens is that you have to find the moment of inertia about the disc. So once you solve for that, we have a weight. Now, initially we tried to use the acceleration due to gravity,
which would have been constant, and we figured out that that was going to be a pretty bad issue.
Yeah, due to the fact that as this is rolling, it's not actually in free fall. It is actually have a tension. So what happens is this has to pull this weight,
to get
uniform disc, to then pull. So that is going to counteract gravity, just like as if you were to hold your hand on it. It increases resistance. So that in turn we had to solve completely for the acceleration instead of having a given acceleration, which would make it easier to solve, because then we could use our typical kinematic formulas as opposed to having to take the summation of forces in the y-axis and the moment.
So once we found the correct acceleration, we were able to then go and find angular acceleration and angular velocity to work towards our final answer.
Hi, I'm going to briefly describe the calculations we do in our project. First, we calculate the theoretical and the actual data to compare and then see what's going on. So first, we drew a free body diagram to know the forces acting on that. We assume that the angular acceleration and then the angular velocity are acting, rotating clockwise direction. And our unknowns were finding the angular acceleration, angular velocity, and acceleration for both actual and theoretical data. For our theoretical data, we use the mass moment of inertia, and also we use the sum of the forces about y equals mass times acceleration at g. So, and also we use the big cylinder and then the small cylinder formula. So we calculate it, and then we got for that angular acceleration is 46.14 radians over second square, and then we got the angular velocity equals to 31.22 radians over second, and then for the acceleration 8.67 feet over second square. As you can see at the bottom of this video, there's like calculations I solve in paper, so as you can see and then see what's going on. And then for the actual, we just count the revolutions per the seconds, we time it, so it's what we got. I think it's not like accurate, That's why it's actual. And we got the angular velocity is 33.23 radians over second. The angular acceleration, we got that it is 39 radians over second square, and then for the acceleration, 7.32 feet second square. And then you can see that it is a 50% error for theoretical and actual, and the very bottom of this video. Thank you.
After working through the measurements and data collection, group 1, our group could able to calculate the moment of inertia, angular acceleration, and angular velocity. After multiple attempts, our results was 15% errors, off from the expected results due to we have only one time of measuring the data, and we weren't having precise timer to do. Also, we assume that the weight of the cylinder is to be the half from the weight of the disc, so it wasn't too precise.